Okay, now we are going to look at the chemical properties of alkanes. We have already looked at the properties, the physical properties of alkanes. We looked at the preparations of alkanes and the natural sources of alkanes. And now we want to look at the chemical properties of alkanes. We want to look at the chemical properties of alkanes. We are saying generally alkanes are unreactive, or they do not easily take part in reactions. In most cases, we need specific conditions to force these alkanes to react. For example, we might need UV light, ultraviolet light, or we might need extremely high temperatures in order to spark a reaction of alkanes. Now we are saying there are three reasons that can explain the reason why alkanes are generally unreactive. We are saying the first one, when you look at the carbon to carbon bond and the carbon to hydrogen bond in alkanes, they are extremely stable to heat. They are thermodynamically stable. And because they are thermodynamically stable, that means they are also strong. And it means if a reaction is to take place, remember, for a reaction to take place, we must break bonds and form new bonds. Therefore, for a reaction to take place, you need to break these bonds, which are strong. Do you see that? That means that you need a lot of energy in order to break these bonds. That's why in normal conditions, these bonds are not broken and no reaction takes place. We are also saying that the carbon and the hydrogen have almost the same electronegativity values. They have almost the same electronegativity values. And because of the similarity in the electronegativity values, it means the bond is not polar. The bond is not polar, i.e. it is not charged. We do not have partial charges here. Remember, in most cases, for a covalent compound, if there is some sort of polarity, that polarity increases the chances of reaction, but since the electronegativity values are low, are almost the same, that means that the polarity is so small and the reaction is, the compound is almost non-polar. The last one we are saying, we do not have lone pairs of reaction of electrons in alkanes. We do not have lone pairs of reactions in alkanes. That simply means that all the carbon atoms in alkanes, they use all their electrons. So we do not have any extra electron that can spark off a reaction, especially with the acids. So here's the reason why we are saying that since these compounds, the alkanes, are not very reactive, since the reaction that they are not very reactive, this implies that we need specific conditions for a reaction to take place. The first one, we are looking at combustion as the first reaction. In that case, combustion simply means burning. So we are going to get an alkane and burn it. One thing is sure, that alkanes are hydrocarbons. That means they have hydrogen and carbon only. That means when you heat, hydrogen will gain oxygen and will become water. Carbon will gain oxygen and become carbon dioxide. Therefore, we can say, generally, if you have Cn, H2n plus 2, this is our alkane. I am burning it. Combustion is burning in what? In oxygen. I am burning it in oxygen. I am burning it in oxygen. Maybe I can put oxygen here. O2 gas. I expect to form carbon dioxide gas and what? And water. I expect to form carbon dioxide gas and water. How would I balance this reaction? Since I have n values, carbon is n, so I put here n. Hydrogen, this is 2n plus 2. 2n plus 2. This is 2. It means if I multiply by n plus 1, if I multiply by n plus 1, hydrogen will become 2n plus 2, which is already 2n plus 2. Now, the last one will be on oxygen. Oxygen, this one, oxygen is n plus 1. Oxygen here is n plus 1. Here, oxygen is 2n. Oxygen is 2 what? Is 2n. So when you add them, what do you have? You have 2n plus n, that is 3n, 3n plus 1. That is 3n plus 1. So you want to write here 3n plus 1 in order to balance the what? The oxygen. Let me see. This is n plus 1 for oxygen. This is 2n, that is 3n plus 1. It means here I have to put 3n plus 1. But now if I put 3n plus 1, you realize that it will be multiplied by this 2. In order to neutralize that 2, I have to divide by what? By 2. I have to divide by 2. That way, the equation would have been balanced. I can have a clear example. If n is 1, that will be CH4. And this will be a gas plus O2. This one is a gas also. Then we form carbon dioxide gas and what? And water. Carbon dioxide gas and water. Since n is 1, this will be 3 times 1, that is 3, plus 1, 4 out of 2, and that is 2. I would have 2 here. Here I will have 1. What am I going to have here? 1 plus 1, which is actually 2. And the equation balances. So this is the general equation which can generate different equations for a given alkane. Okay. Maybe when n is 2, let's look at when n is 2. That will be for an alkane of ethane. This is methane. So ethane, it will be C2H6. C2H6, this will be a gas plus. Now this will be 3 times 2 plus 1, that is 7 out of 2. 7 out of 2. That will be 7 out of 2. Or oxygen. And this will give us, that is 2 carbon dioxide. 2 carbon dioxide plus, this will be 3 water. 3 water. Whereas sometimes you can choose to multiply by 2 everywhere in order to avoid the what? To avoid the denominator. So I'll have 2 here, then this will become 4, and this will become 6. But even the other reaction is also correct. The second reaction of alkanes is chlorination. That is the reaction of alkane with chlorine. This is only possible in presence of UV light, ultraviolet light. However, if you have high temperatures of 250 to 400 degrees, the reaction can also take place. However, the products here are so many. I.e., if I use an example of methane, I'm using an example of methane. Methane is CH4. This is a gas. If I react it plus chlorine in the presence of UV light, I can have one of the chloride atoms replace hydrogen, and that it will be CH3Cl. But I can also have, when 2 chloride atoms have replaced 2 hydrogen atoms, and that will be CH2Cl2. I can also have, when 3 hydrogen atoms have been replaced by the chloride atom, and that will be CHCl3. But I can also have CCl4, CCl4. So this reaction sparks or results into many products, and these products, it is not possible to separate them. It is not possible to separate them. They just remain the way they are. And if we are to show how these products are formed using a mechanism, then we are going to follow what we call a free radical mechanism. Free radical mechanism. So let's look at the mechanism of this reaction. A mechanism is simply a series of reactions that shows how a complete reaction takes place. How a complete reaction takes place. For example, I'm going to be reacting in the first place. I'm beginning with methane and chlorine, but now chlorine will be first attacked. So I will have this is the chlorine molecule, which has two atoms, Cl2, and because of the presence of UV light, this is going to split into radicals. If we are splitting a bond into radicals, we must use half arrows. These are called the half arrows. They are not complete, they are half. And that means that we are going to form two chloride atoms that are identical. But now remember, like we said, a bond is a pair of electrons. It means a bond, which is a pair of electrons, has been shared by these chlorine atoms. Each chlorine atom has taken a single electron, and that electron we shall represent it as a dot. That means now that we have two chloride atoms, each has taken a single electron. Now, one of these radicals of chlorine with single electrons is going to come and attack the methane gas. So in that case, we shall have C. So I can put here H3, and then I create here H. This and this are the same. CH4. It is reacting with one of the radicals here. Now this C electron is going to spark off a reaction. With this electron pair, which we are calling a bond. So this electron pair is going to also be forced to be split. And then one of the electrons will come to react with the chloride, and then this other electron will remain on carbon. And this will lead to a formation of hydrogen chloride, and then we shall remain with CH3, which has a radical. So the CH3, this carbon has remained with the radical because one of its bonds was broken, and it has remained with a single electron, causing it to be a radical, and now this one has become HCl. Now, in that case, now this radical is going to react with the excess of the chloride radicals. In that case, we shall have CH3 radical and then the chloride radical. In that case, this one will bring its electron, even this one will bring its electron, and then we will end up forming CH3Cl. This will be our first product, and this will be its byproduct. That's what I was saying, that this will be our first product. This will be our first product. However, the reaction can continue now with the chloromethane in this case. And I want to illustrate it. You will allow me to wrap this. I hope you can remember it. So we are saying we have formed chloromethane. However, this chloromethane can still be attacked by excess of the chloride atoms, chloride radicals, in this sense. We are having carbon, so the chloride, I can put it here. here I can bring my H2, there are 3. I will just have to use the third one. So we have Cl. I am having CH2 here. I bring another H here. As long as the radicals are present and the reaction is possible, the reaction will continue. The reaction will continue. This one will bring it single electron, and this one will also split into a single electron that will go with hydrogen, and we shall have this other electron coming to what? To the carbon. In that case, what shall we form? We shall form, this shall remain as H2 with our Cl, but now has a what? Has a radical. Why? Because this electron, the single electron, is now on the carbon, and now this one has gone away as HCl. So you realize that every time the radical comes in, it liberates hydrogen chloride gas. In that case, this radical, because we know that radicals are extremely reactive. They are extremely reactive, and because they are in a solution, in a reaction mixture, they will always be the ones to spark off a reaction. So I have this radical here. It's going to attack the excess of the chloride atoms, chloride radicals, So this will come here, and this one will also come here. Remember to use half arrows, and we shall end up forming CH2 Cl2, which is actually our second product. But we are saying even this compound can still be attacked by chloride radicals. Remember, there are so many in the reaction mixture. In that case, we are still going to have C. I will just bring my H here. Maybe I can bring Cl. Even here Cl. Then here I still have my hydrogen. I still have my radicals. So this one will bring, even this one will bring. Then this radical will form on there. The single electron will come on the carbon. And in that case, I shall have the carbon now with the radical, but with still one hydrogen and the two chloride atoms. Of course, plus HCl that goes away. Now this radical here is going to react with the excess chloride atom radicals, and we shall have Cl2 radical, and then the chloride radical. This one comes here, even this one comes, and then we form CHCl3. That is our third product now. But we have said that the reaction has not stopped yet. We are going to continue still with the formation of tetrachloromethane. This one is dichloromethane because of 2. Now this is trichloromethane. Now we want to see the formation of tetrachloromethane, because still trichloromethane is going to still be attacked. By the what? By the chloride radical. In that case, so we'll have this and that, and then that. And we shall end up forming Cl3 radical still with the HCl. Now that radical is going to react with excess chloride radicals. Then they pair. When they pair, they are going to form tetrachloromethane. So we are saying that this reaction, it forms different compounds, so a mixture of compounds. We have chloromethane, we have dichloromethane, we have trichloromethane, and tetrachloromethane. And we are saying all these compounds are present at the same time, and it is close to impossible to separate them. That's why in most cases especially when we are looking at synthesis reactions, we advise students to avoid this reaction because this reaction does not give us a specific product. It does not give us a specific product. So the previous reaction can also occur with other halogens. However, the degree of reactivity decreases as you go down the group setting. We are looking at the last reaction of alkanes. There are many other reactions, but we want to look at only these three. We are saying alkanes react with nitric acid via free radical mechanism, just like chlorination. And in that case, we are saying, for example, if I have methane, okay, let me in this case use ethane. Let me use ethane plus nitric acid at 400 degrees Celsius will form CH3CH2 NO2. Of course, we are going to have the water molecule as a byproduct. Let us look at the mechanism. Here of the reaction. In that case, we are going to begin with the nitric acid. Nitric acid is more of like this in its structure is like that. In that case, this bond is going to undergo radical splitting, or is going to split, whereby one of the bonds of the electrons will go with the oxygen, then the other one will go with what? With nitrogen. Because if they are splitting the bond into radicals, I said we use a half R. In that case, we shall form OH radical, then plus NO2 still radical. Now, this radical here is going to come and attack one of the bonds here. So in that case, we have CH3. C, I can call it C, then I put here H, then I put here H, then I put here H. That is CH3. I have my OH. So this OH will spark off a reaction between the carbon and hydrogen bond, splitting it into radicals. In that case, we shall form, that will be CH3, CH2 radical, then plus what? Plus water. Of course, when the OH goes with hydrogen, it forms the water. Now, this ethyl radical is going to react with the nitro radical. In that case, we shall have CH3, CH2 radical being attacked by NO2 radical, and they will spark off a reaction leading to the formation of CH3, CH2, NO2. Just like what I said there, of course, the byproduct will be